Let's talk about kidneys. So you may look at us and say, hey, that's not a kidney. And I'd say, you're wrong, it is, just blown up. So this whole thing here, what we got going is called a nephron. Ooh, that's a bad glare. Let's try it again. This whole thing is called a nephron. The whole point of a kidney is to take things out that we don't want and put things back into our blood that we do want. So at this point here is called the glomerulus, and this is where initial filtration occurs, but we'll come back to this. Point being is a whole bunch of stuff's going to enter our blood system. So I have this drawn a bit funky. So this looks like a track of the kidney, the tubules itself, but what this is really representing are the cells of a kidney. So the tubule actually exists on this side, and then the blood exists on this side. And then this is the epithelial kidney cells that have the transporters on them. Since the tubule is actually a little tube, it's a space, the transporters have to exist in the membrane of the epithelial cells. So when we have anything coming from here, it's leaving the kidneys, and anything coming from here to here is going into the blood. When stuff gets put into the blood, we call that reabsorption. When stuff leaves the blood and goes in the tubules, we call that secretion. It's all from the point of view of blood. So blood being the primary character, in the story, the blood reabsorbs or the blood secretes, even though the kidney's the one doing the action. That being said, there's a lot going on here. There's a lot to unpack. We're going to break it down piece by piece. So this is called the proximal convoluted tubule. On the proximal convoluted tubule, this is where 90% or 70% of our filtration is done. So for, I would say, the glomerulus over here allowed a whole bunch of stuff in, and all the good stuff as well, like glucoses, lactoses, amino acids. We're going to need to pull those in. So we're going to do that through a symport of sodium and glucose. Now, I did get a little ahead of myself. I need to start by saying that every single point along here that we're going to talk about has these sodium-potassium transporters and sodium-potassium ATPase. These are the only things that are actively consuming ATP as far as ion transport goes, because we're relying upon this primary active transport to fuel all these secondary active transports. So unless I say otherwise, every single one of these is a secondary active transport. So because we establish a high gradient of sodium, or let's say you drink you just have a lot of sodium in your peak, sodium comes through, or the tubule. So that's going to come in via secondary active transport because the glucose wants to come in, and then we're going to pump sodium out. And in turn, glucose, lactose, and amino acids are also going to be pumped out as we pump sodium in, since that sodium's natural gradient wants to come in. Sodium, again, is going to have a gradient coming out, but we're going to use that antiport because hydrogen ions actually have a larger gradient coming out. So we're going to use that to bring sodium in to fuel our transporter here. We have another one coming from the tubule where, again, NH3 is coming out and sodium's coming in. Now, this transporter is the exact same thing, but here we call it the distal or the proximal convoluted tubule, and this is the proximal straight tubule. But they both have these NH3 transporters on them. Still on the proximal convoluted tubule, we have a transporter called MBC, which allows bicarbonate to come back into the blood since we need bicarbonate for our buffering system. And it also supports sodium. So we're attaching sodium's natural concentration, we're attaching sodium to the concentration gradient of HCO3, and that pulls it out. On the straight tubules, we have a KCC transport that stands for 1 potassium and 2 chloride anions. So they're going to be reabsorbed back into the blood. Potassium is going to, which one's driving the gradient here? You know what? The chloride anion is going to be driving the gradient in this scenario. That's going to pull both those out. Now, we have water. I shouldn't say now we have water. Water's actually been here the whole time. We often talk about this section this section is called the loop of Henle. We often talk about that. This is where water filtration occurs. But really, the vast majority of the water filtration is going to occur through these cells and actually through gaps in these cells as well. So it's going to make a mess of my picture, but we're going to draw an arrow through there. And even where there isn't a gap, I'm going to draw an arrow because it's able to go through regardless because these cells aren't tight knit yet. The reason why we say water filtration happens in the descending loop of Henle is because that's all it can do. It only can filter water, nothing else comes with it. It is important to note that we also have solvent drag where we have potassium and calcium ions that are stuck in the water coming from the tubule, and that those get drugged with it and get reabsorbed into the blood. We say the important thing of the loop of Henle here is that as we decrease here, or as we come down the loop of Henle, we're actually increasing our osmotic gradient. So for example, on the blood side of things down here, we're actually getting up to 600 milliosmol, which is 300 more than we typically see. Inside a different type of kidney cell, something called a juxtamedullary cell, this goes even further down into the medulla of the kidney, and that's going to get up to like 1200 milliosmol, which is crazy high, but we'll talk about that here in a minute. For reference, this type of kidney cell, which makes up the vast majority of them, is called a cortical kidney cell. Once we hit a breaking point here, I'm just going to draw a line, even though a line doesn't actually exist. This is where we get into the ascending loop of Henle. The big point here is this is where all of our kidney cells is no longer permeable to water. So they actually get the stitching in between each of these cells where now water can no longer flow through it, but it also can't flow around it. And the same is true as we go up this, our osmotic gradient is actually going to decrease. What we are seeing here though is not only do we have our Na potassium pumps, we also have two more kinds of pumps. One's called an NKCC, I'll write that right here, and that's coming from the blood. NKCC. And we have another one right here that is called the AE2. Can't forget about the AE2. So the NKCC, for lack of room, I'm not going to draw these arrows, but we can see pretty similar to what the KCC did, is now we just have an N standing for sodium, because its element is Na. So we're bringing in a sodium, a potassium, and two chloride anions. Then, because of this gradient that was established here, we're actually going to pump out, making sure. Yeah. So now we have chloride anions, and chloride anions and potassium ions, or cations, can leave through leak channels. Here, we're going to pump in chloride anions, and we're going to pump out bicarbonate. And that's going to decrease the osmolarity or the osmolarity concentration inside here, making it less osmotic, less filtered. No, more filtered, but less concentrated. Less concentrated, but more concentrated with the stuff that we don't want. It's confusing, but that's the idea. Then we get to our distal convoluted tubule, and it has an NCC, so now we're bringing in one sodium and two chloride anions, and we're pumping out still more sodium and potassium just like we were before. But there is one important factor here. We have macula densa cells. So let me draw a stick version of a kidney. Let's see, that wasn't very good. Let's try again. So if this is our distal convoluted tubule, this here is also our distal convoluted tubule. Right in this region, right here, right where we attach the glomerulus, we're going to have these macula densa cells. What they're doing is they're monitoring GFR. GFR being is how many liters per second how many liters per minute of blood or blood plasma are we able to clear through our kidneys, starting at the glomerulus. They're going to monitor GFR. If GFR were to drop, they're going to excrete things that are going to cause vasodilation because they're saying, hey, we're low, we need to get more blood pumping through. So they're going to release things like paracrines, like nitric oxide, for example, causing acute vasodilation. That's their whole job in life. we have the NCC, we have the ATPase, and then over here we're actually going to have our more options to cause water to leave. But the directions are to talk about that in a different video. So we'll just say in the collecting ducts we can cause more water to leave and more salts to leave if we need to. There's an important concept over here I want to talk about with our glucose, lactate, and amino acids. So in the tubules up here, we have, all these are done via transporters or transport channels. So glucose, lactose, and amino acids, so long as sodium is present, they're allowed to come through. But there is the possibility that we cause a surplus of, we have a surplus of sugars that all the transporters or channels are completely clogged up. What this would result in is we don't end up resorbing all the sugar, and it's going to come out as excretion in our urine. Now, for a healthy individual, this should never be a problem, but for someone with diabetes whose blood can't process or whose body can't take up the sugar, they will see an overwhelming amount of sugar, and these transporters will get overwhelmed, which will then in turn cause them to excrete some of those sugars that their body's needing. Same thing applies for amino acids, lactases, anything that has transporters that can be overwhelmed.